things. And this is going to be important in a second to go full physicist here on this problem. I already have to laugh. It's so amazing. Everything's a harmonic oscillator if you're brave enough. A huge thanks to my Patreon supporters for making this episode possible. Good morning, fellow mathematicians! Welcome back to another video. Today we are going to go full physicist. We are going to go by the motto, everything's a harmonic oscillator if you're brave enough. It's going to be absolutely fantastic. So this right here is going to be experimental physics at its finest, also theoretical physics. We're going to take a look at the second part of my marble rotating on a table video. Watch the first part if you haven't done so already, link in the description. Just a little flashback. We had two masses being connected by a string. There was a hole in the table and we were giving this thing a big nudge, okay? And it's going to start rotating. And we found out the equations of motions using Papa Lagrange. And today we want to ask ourselves two questions. When does M, so the small mass up here, trace out a circular orbit around the hole? Okay, when does it have a stable circular orbit around this hole, tracing out a circle? And then the second question is, when this mass M is going to trace out this orbit, and we're going to go to the table and we're going to give it a slightly small nudge, okay? We are going to add a bit of noise to this whole thing. This just screams for basically calculus of variations. Give M a small nudge, show that the circular motion that it has up until now is still stable, so it's going to get back to its circular motion basically. And what is its frequency? This is what we are going to talk about today, but before we get into the main video, don't forget to check out today's sponsor, Raid Shadow Legends, once again, who were kind enough to sponsor yet another video here on this channel. Once again, I would like to present Raid Shadow Legends to you, and like mentioned in the last sponsored video, I'm actually a big fan of MMORPGs. I played Guild Wars basically my whole life. I was playing Pokemon when I was young and many more RPGs over the course of my lifetime. And Raid Shadow Legends actually gives me a new perspective on turn-based RPGs. Next to their over 500 champions that you can basically unbox using shards, there also come 13 factions with them. And my most favorite factions are the corrupted ones, also called the undeads. And they're actually pretty cool because they remind me so much of the Guild Wars 2 Titan minions, and this is something that really makes it even better for me, because they're also called corrupted here and they share similar traits to those in Guild Wars 2. Next to them being the evil counterparts to all the other factions that you get in the game, I also just love how they look with their flesh hanging down, with the skeletons popping up. And also we got dark elves. I mean, who doesn't love dark elves? Other than that, there are many other reasons to start playing Raid Shadow Legends today. On the one hand, we got over 500 champions. You can mash them together into teams and just play with them during different campaigns and the like. And you can also do faction wars and clan wars, etc. Really nice. Also, they got daily rewards, so who doesn't love daily rewards, right? And probably the biggest reason why you should start playing today is their new Doom Tower. They just put out their biggest update ever this month, and it's a giant tower with 120 floors, bunch of secret challenge rooms and a lot of bosses. And by a lot, I mean a lot. I mean, we got 120 floors. That's a lot of bosses to clear. Also, next to the Doom Tower, Raid Shadow Legends always puts out new champions. 13 new champions this month, and also, if you use the link at the top of the description, you are going to get the secret special champion Bulwark. That's absolutely amazing. He's an absolute powerhouse and is going to help you immensely in the fight against all the bosses in the Doom Tower. And next to Bulwark, you're also going to get an XP booster, 50 gems, some energy refills, and also an ancient chart to unbox another champion. So this is going to give you a nice head start into Raid Shadow Legends if you start playing today. So if you feel like Raid Shadow Legends could be something for you, then please make sure to check out the link at the top of the description and download the game. It's going to help out the channel like a lot, like the edges of the screen a lot, okay? I hope you understand. So check it out, download the game and support the channel this way. I'm going to see you online, and now we are going to dive right in. So at first we are going to take a look at the first question. When does the small mass M trace out a circular orbit? Now what does it mean to for something to have a circular orbit, let's think back to the definition of a circle. So given a midpoint or center of the circle, each and every point on the outer arc is going to be the same distance away from the center. Meaning our radius is never going to change. That means our radius, that wasn't a normal case, time dependent right here, is going to be a constant. And this is the exact point that we need to take into consideration. Namely, this happens when r is constant. Okay, if r is constant, that means it's not time dependent anymore, meaning if we differentiate a constant with respect to time, just like up here, it's going to be equal to 0. Meaning our r dot is equal to r double dot, which is going to be equal to 0. Hey, that is cool, right? Because our differential equation right here is going to be way easier, okay? Now, meaning we're going to turn this, okay, this part is going to vanish. We're going to say that 0 is now nothing but m, our r, okay? We are going to give this r a new name because we want to find out the exact radius when we trace out a circular orbit. Let's call this thing r naught times phi dot squared minus m times g is going to be our exact equation. Now, we are going to go a step further now, and we are going to take a look at what we have up here. Namely, this was one of the most interesting points in my opinion. Namely, if we take the time derivative of what we have in here, it's going to be 0. What do we have in here exactly? Well, if you have watched my video about the effective potential, you might notice that this right here is nothing but the angular momentum. If we differentiate some structure in physics like energy, or let's say the angular momentum with respect to time, and it's going to spit out 0. On the one hand, that means that the angular momentum is constant, but on the other hand, that means that angular momentum in this system is going to be preserved, which is really cool. Conservation of angular momentum is going to be coming into play here. Meaning overall, okay, we differentiate with respect to time. This is going to lead to m r squared. Phi dot is hence nothing but a constant angular momentum L. Okay, and now we can basically solve for phi dot, meaning phi dot is hence nothing but L divided by m r squared. And basically, if we put our r back, okay, it's still in the system basically. We are going to give r the new name in a second. We can just plug in our phi dot, our new definition. Meaning, if we bring m times g to the other side, mg is hence nothing but, okay, we are going to have m times r. Phi dot squared is going to be nothing but, by new definition, a squared divided by m squared r to the 4th power. So m and m squared is going to cancel out, r and r to the 4th power is going to cancel out. Meaning overall, and now we are going to give it the new name, r dot, r naught, namely capital M times g, is hence nothing but, okay, a squared divided by m r naught to the 3rd power. And well, now we can proceed with finding out what the radius is for us to have a stable circular orbit. Namely, what we are going to do is just we are going to solve for r naught. Okay, we are going to take the 3rd root at the end. We're also going to take the reciprocal here, multiply everything by L squared under the condition that it's not equal to 0. It would be equal to 0 if, for example, our radius were 0 or m is 0, but then we wouldn't have this problem in the first place. So it doesn't happen. Our mass m, we don't want it to be equal to 0, otherwise that would also be equal to 0, blah, blah, blah. Meaning overall, r naught is hence nothing but the 3rd root of, okay, we are going to have, let me see for a second. We are going to get our L squared to the numerator and then m times capital M times g down here in the denominator. And hence we are done. This right here is the radius to have a circular motion, which is kind of cool, right? I mean, yeah, it's cool that you can calculate something like this. And now we are going to take a look at the second part. We are going to give m a very small nudge, show that the circular motion is still stable. When you have a circular motion which is still stable, what physicists are striving for is a harmonic oscillator, basically, because a harmonic oscillator is going to take a look at very small oscillations of a system, and harmonic oscillators are by definition always stable, which is a cool thing. Meaning, we are going to give a small nudge to our m. So what does it mean for something to give it a small nudge? I mean, our radius r naught that we had initially is going to turn into, okay, we had a circular motion, and now we are going to give it a tiny little touch. Meaning our radius r naught is going to be basically displaced a tiny little bit. It's just like with calculus of variations. We are going to take a look at small variations, errors, noises in our original motion, meaning r naught is going to turn into some new r with respect to t, which is going to be defined as nothing but, okay, we are going to take our r naught, but we are going to add a little bit of noise to it, meaning some delta with respect to t. But this noise is extremely small. Small means if we have delta squared terms, they are going to vanish. They are so small, they are really negligible in the grand scheme of things. And this is going to be important in a second to go full physicist here on this problem. I already have to laugh. It's so amazing. So at first, let us take a look at what happens if we differentiate both sides twice with respect to time, for example. Because if we take a look at this equation, we need r double dot in some case. I mean, r double dot is hence nothing but, okay, our r naught is a constant thing. It's all of the things that we have here are constants. This right here, this L is a constant, M, and G are also constant, meaning r naught is also constant, meaning it's going to vanish when differentiating with respect to time. But obviously our small nudge, our noise, it's going to be a time dependent function, meaning this is going to be equal to d double dot, delta double dot. And now we can basically plug what we have into here, meaning overall we're going to have that m plus m. Okay, r double dot is hence nothing but delta double dot is hence nothing but, okay, we are going to get, let us plug everything in and then let's see what we are going to get. I mean, this right here is going to turn into L squared divided by m times, we're going to take a look at the regular radius, basically. Oh, okay, this new radius that we're going to have here. I have to think about everything. It's kind of, haven't done this in a while. Let's put it like this. Meaning our r is nothing but r naught plus delta, but all of this to the third power. After all, if we take a look at basically what we have here. Okay, this is just this reformulation, and this is basically it. We don't have this m factor in the front, and then negative m times g. Okay, now we are on the right track yet again. This is supposed to be a plus. And now we can start doing approximations on this whole thing, because you see we have this cube term down here in the denominator, and we can actually expand this a tiny little bit, okay, using just binomial theorem. This r naught plus delta to the third power is overall at first nothing but, okay, we have r naught to the third power plus, and then we have 3 r naught squared delta plus, and now here's going to come the best part. We're going to get 3 and then r naught delta squared plus delta to the third power. And like I said before, this nudge is really, really small. If you have squared terms, like in O delta squared terms, basically, you are going to have them being negligible. Really, they don't really matter for our approximation, actually, okay, because the nudge is already so small that if you take it squared, it's going to go to 0 way, way faster than all the other terms. Meaning this is approximately r naught to the third power plus 3 r naught squared times delta. And now we can start plugging all of this into here. Let us do a bit more manipulations on this whole problem, meaning 1 divided by, and then we are going to have r naught plus delta to the third power is going to be approximately 1 divided by r naught to the third power plus 3 r naught squared delta. And now we are going to factor out the r naught to the third power, meaning overall this is going to be equal to 1 divided by r naught to the third power times, okay, then we are going to have 1, and all of this is going to be plus, and now we are going to have 3 delta divided by r naught. Now we are going to go once more step further, because we want to have all those delta terms vanish down here. What we can do basically is we can turn this right here into a second order term basically. For this we are just going to expand numerator and denominator by the conjugate of this thing, namely 1 minus 3 delta divided by r naught divided by 1 minus 3 delta divided by r naught. Meaning this part right here is going to be the difference of two squares. It's something like 1 minus delta squared, and we just said that terms of those kinds are going to vanish for small nudges. So this delta squared is going to go to 0, meaning overall in our approximation we are going to get that this whole term that we're having here, 1 over blah blah blah, is approximately, you can justify this more by doing a Taylor series expansion of this term, okay, in 1 over the third root basically. It's going to be approximately 1 minus 3 delta divided by r naught divided by r naught to the third power. Yeah, everything's a harmonic oscillator if you're brave enough, and this is going to apply right now at this very moment. We're going to plug everything into here. We're going to get that m plus m delta double dot, and then we're going to bring everything to the other side. We're going to have minus L squared divided by m, and also what we are going to have is R naught times 1 minus 3 delta divided by R naught, and also plus m times g is going to be equal to 0. Now we can start factor everything out. I mean, if we just multiply this into here, this whole part, L squared divided by m R naught, is going to be a constant, plus another constant, and their dimensions are equal, are going to result in another constant. Also, we can divide both sides by m plus m, it really doesn't matter, and dividing this new constant by another constant is going to result in yet another constant, meaning we are going to get delta double dot. Then we are going to get plus something, and then plus some constant c is equal to 0. What is this other something that we are going to have? I mean, we are going to divide everything by m plus m. Now we are factoring this out. We are going to get negative times negative is positive. We are going to get a 3 up here overall. Also, we are going to get a delta term here, which is the really important part at that. Also, what we are going to get, I forgot the third power term right here. We are going to get R naught to the third power, and also a small m down here, and an L squared here. And this right here is a simple harmonic oscillator. This is something that you need to see at this point. And if you're wondering what about this is a harmonic oscillator because of the constant, just think about the spring system. Okay, if you have a regular spring going on, for regular spring, you are going to have that, okay, we are going to have a certain force applying, mx double dot, on what we have here is hence nothing but, okay, if we consider a damping term at that, so on the one hand we have that our mass is going to be dragged down by our gravitational force, m times g, but also on the other hand it's going to be dictated by Hooke's law, k times x. And now you might see the basically our similarities. I mean, we have some x double dot term right here, which is delta double dot. We have some constant, so k divided by m basically after that times our delta or x, and then we are going to have plus some other constant, which is going to be g in this case. And it's the same case here, and we all know that the spring system is basically a harmonic oscillator overall. And this is quite cool, right? And you can actually see at a glance what the frequency is going to be. I mean, this right here, obviously, if this right here is, for example, some distance, differentiate with respect to time twice, that's going to be an acceleration. But this right here is just a distance, meaning this part must be something of the form 1 over second squared, and 1 over second squared is just a frequency or the eigenfrequency of the system squared. Meaning overall we know that omega naught squared, so the frequency that we still need to find out, is nothing but this. Meaning overall our omega naught is going to turn into the square root of 3 L squared divided by m plus m times R naught to the fourth power. We are going to get a fourth power term right here because of this R naught times m. And also you can split this up a tiny little bit more because we know by this equation right here that our L squared divided by m R naught to the third power is m times g, meaning overall this right here is going to turn into the square root of, okay, we are going to get 3 times capital M divided by m plus m times the square root of, okay, and we are going to be left with, we are going to get an R naught term down here, and also we're going to have a g term here. And this right here is the frequency of our system. And here, this basically concludes the less complementary video on this physical problem. You can justify all of this a bit more rigorously. Okay, you can't really call this right here rigorous. This is just physicist argument, but I want to include something on this channel too, like this. You can justify all of this way more by using the effective potential, because the effective potential works when you have, for example, an angular momentum involved, which we have and which is constant at that. And you can differentiate the angular momentum twice to get a very nice expression for the harmonic oscillator overall. So I leave it as an exercise to the viewer. If you really want to see see it, I can make another video on that basically. But yeah, this concludes everything I have to say up until now. Don't forget to check out today's sponsor, Shadow Legends. You can really support the channel that way, okay? You know, clicks convert into hopefully having the sponsor for a longer amount of time here on this channel. And other than that, thank you guys for watching. Don't forget to subscribe to the channel. Until next video, I wish you guys a flammable day. Ciao!